So now that we know how to make a power series, a geometrical power series, we're going to look at the basic operations we can do with the power series. And the operations are a lot like the operations for our real number system anyway. Taking a function, multiplying it by k, just if we multiply every term by k, then we're going to multiply k through each term n times. So we have that multiplying factor there. If we take a function to a power, then we're going to factor that power through the entire series. We can add and subtract series just like we add and subtract real numbers. So not too much different than what we see at the real number system. So here we have two power series. We can add them together. And so if we look at this just from the fact that this is in our a1 minus r form already, then for this first one, we have an a equal to 1 and an r equal to -1. Here we have an a equal to 1 and an r equal to 1. So we're looking at a series here as n goes from 0 to infinity of 1 times -1 to the n, plus another series as n goes from 0 to infinity of 1 times 1 to the n. And so as we add these two series together, we can do that one of two ways. We can either add these together, like adding and subtracting these two series, or we can add the two fractions together and rearrange it in this form for a geometric power series. And so I'm going to go ahead and do that. So looking at adding these two things together, common denominator would, by getting their common denominators, we're looking at adding those two expressions together. So we'd have to multiply this by 1 plus x and this by 1 minus x. And so when we do that, you're looking at 1 minus x plus 1 plus x. So this is 1 minus x and this is 1 plus x all over this denominator. And when we simplify that, this entire numerator becomes 2. And the denominator becomes 1 minus x squared. So it gets into this geometric sum of a geometric series expression just by simplifying it. And so we can rewrite this geometric series then as 2 times x squared to the n power, right? This is a times r to the n. And so there's our geometric power series for those two individual series added together. And so we could just rewrite that as 2 times x to the 2n power. Now we can see how this becomes a geometric power series here. So it becomes apparent that we can get this power series expressions for the entire expression, for the entire addition process here. When we take a look at this, just to kind of take this one step further, we can use the property of series to simplify it a little bit. We can go ahead and pull out, kind of like where we add these two things together, we can go ahead and take these coefficients and add them together. So we can really take the fact that we have this -1 to the n and 1 to the n. And so if we look at that, we really have kind of a -1 to the n plus 1 to the n um, excuse me, yeah, this would be x to the n. Excuse me, I said that wrong. This should be x to the n. So if we have that times x to the n. So this is, this is really, if we look at this, this is really 1 times negative 1 to the n times x to the n. So we really have a negative 1 to the n, and then this we can really call this, just to be consistent, 1 times 1 to the n times x to the n. And so we really have a negative 1 to the n plus a positive 1 to the n, x to the n. And so when you look at this expression, when you look at these two expressions for 1 and negative 1, when n is odd, the stuff in the brackets equals 0, and when n is even, the stuff in the brackets equals 2. And so that's how we know that we get these even powers here, and we get a starting value of 2 when n equals 0. So if you can make this leap here, you can take this shortcut. Otherwise, you're just going to have to go ahead and add the power series together. To find a power series for natural log of x, we have to find a power series. We need to get a function that looks a lot like a rational expression, that looks like the sum of a geometric series, so that we can write it as a power series. And this doesn't have any rational characteristics to it, but if we take the derivative of x, then we know that that's 1 over x. We start to get this rational sort of characteristic. So if we take the derivative and get 1 over x, then we can start to rewrite this expression, 1 over x, as in this form, and get a power series for this. So we'll call this g of x. We'll let g of x be the derivative of f of x. And so if we now go ahead and re-express this, we want to center it at 1. That's important, because if we look at this rational expression, it's not defined at 0. So you definitely want to center it at 1. So you know you want an x minus 1 expression, so that the center is appropriately noted. I'll put a 1 in the numerator, because there's a 1 in the numerator up here. We'll start with that. We really have a 0 here. And I know I want a minus, but right now we don't have a number out here, so 0 seems appropriate to start with. Okay, so what do we have now that I've kind of modified the denominator? Well, I have a minus x and a plus 1, which is not mathematically equivalent to what we have up here. I need a positive x, so I'm going to go ahead and write this as minus a negative, because that'll get me a positive. Anything I can do that's mathematically valid to get to this point, I can do. So how does that change us now? We have minus a negative x, that's a positive x, that works, and we have minus a negative 1. So all of that is a minus 1. So if I have a minus 1 in the denominator, I'm going to want to add a 1 in the denominator, just so that we get back to a value of 0. So now I have something that's mathematically equivalent. I've got 0 plus x minus 1 plus 1. And that's just equal to x. And so I'm going to go ahead and rewrite that then. This 1 out here is handy, because I do need a 1 in this position. So it's 1 minus a negative x minus 1. So I have, just so happens at the top, it also happens to be 1. So if I write this as a power series, n equals 0 to infinity, I have my a, which is 1, and my r, which is minus the quantity x minus 1 to the n power. And so there is my geometric power series for g of x, for 1 over x, centered at 1. Now, what I need, though, is f of x. I need an expression for the natural log of x centered at 1. And so if I want an expression for the natural log of x, then really what I have to do is I have to integrate g of x. to get that. And so when I integrate this, if we're going to integrate that, that expression, then we're looking at integrating it with respect to x. So we have an x to the n power here. We have to deal with it. I'm going to rewrite this. This value of a being 1 is something I really don't have to express, that coefficient. But I do have a -1 to the n here, so I have, I'm going to keep it here just for one more step. Then I have a -1 to the n, and then I have an x -1 to the n. So if we kind of look at inside the brackets here, I've got a -1 times x -1 all to the n power. That's kind of what all that means. And then now I'm going to drop the first term, that a value, just because mathematically speaking, we don't need to have it there, just to make it look a little simpler. So g of x, the power series for 1 over x looks like -1 to the n times x -1 to the n. So that's what I'm going to integrate. -1 to the n, x -1 to the n dx. Okay, so as I integrate this, really, when I'm integrating it, it's this part that we really have to integrate, because that's where the variable x is. So that's what we really need to integrate. So integrating that, then just pull out the summation sign. -1 to the n just is a constant that gets pulled out. So integrating this, you got to bump up the power and divide by that new number, so that's n plus 1. X -1 to the n plus 1 power. And then the chain rule inside here is just another value of 1, so that's not going to change it. So here is the here's the power series for the f of x, which is the natural log of x. And we also, of course, when we integrate, I have a derivative. I'm not sure if that was a stray mark or a derivative mark there. Either way, it shouldn't be there. So so there is the power series for the natural log of x. We also have a constant, though, of integration, right? When we integrate, we get a constant of integration. So if we're talking about the center of x equal to 1, we have to kind of figure out if that constant of integration is anything but 0. So if we think about this, for centering it at 1, what we're saying is let's evaluate this at an x value of 1. So to figure out that constant of integration, at x equal to 1, the natural log of 1 is 0. So coming back up here, then we have 0 equals, if I put 1 in here, this whole thing is 0. 0 plus c. So c does end up being 0. So we really have the power series expression then for the natural log of x ends up being this expression, -1 to the n, x -1 to the n plus 1 all over n plus 1. For this one, it's asking to find the sum of the series. So when we look at this, we have to kind of take a look at rewriting it, really. So if we kind of look at this as rewriting it of something to the effect of, first of all, this starts at 1. If we want to find the sum of a series, we got to start at 0. So we have -1 to the n plus 1. We have 1 over n times 1 over 3 to the n. So we have something that looks kind of like that. And so we have to write this at 0, so we have got to back this up a little bit. And so, you know, how do you want to do that? well, we need to rearrange it. And so if we look at this in terms of just kind of writing out the first couple of terms, when n equals 1, this is 2, so this would be minus 1 squared, 1 over 1, 1/3 to the first power, and then minus 1 cubed, 1 over 2, 1/3 squared, plus minus 1 to the 4th, 1 over 3, 1 over 3 cubed, plus minus 1 to the 5th times 1 over 4. This is when n equals 4 times 1/3 to the 4th. And so if this has to now be the 0th term, and this has to be the first term, and this has to be the second term, and this has to be the third term, then we are looking at a power series starting at 0 of, let's see, we got to have a positive 1, so we need a negative 1 to the n. This has got to be 1. So we're looking at, this has got to be 1 for the 0th term, 2 for the first term, 3 for the second term. So we're looking at n plus 1 instead of just n. This has got to be 1 bigger than the index number, 1 bigger than the index number, and so forth. And this has to be 1 bigger than the index number. So we're looking at 1/3 to the n plus 1. And if you notice, now that we have it rewritten starting at 0, because in order to find a sum of a geometric series, that's got to start at 0. If you notice, this also ends up being the integral of the original series, right? If we did the power rule on this, we would bump up this power by n plus 1. We would divide by it. There it is, bumping up the power by n plus 1 and dividing by it. Okay. And so we end up with basically doing an integration process just by rewriting the terms and finding the new pattern. So I could have just integrated it as well. Now, if we talk about this series here, you should know that this series looks like the natural log of x plus 1. The natural log of x plus 1 looks like minus 1 to the n, x to the n plus 1 over n plus 1. So that's the natural log. And if we look at this, then, and we rewrite that, so actually let me do this. So this is also another series that we really have to be pretty familiar with, its expression. If we take a look at this then, and we kind of rewrite it to look like this, we would say n going from 0 to infinity, minus 1 to the n, we got that. And if I put this in the numerator, it would look like 1/3 to the n plus 1 all over n plus 1. So as we write it like this, we can see then that x from this expression is where the 1/3 is from this expression. And that being the case, then, if this is the natural log of x plus 1, then this over here must be the natural log of 1/3 plus 1, because the 1/3 is where the x is. So the sum then must be the natural log of 4/3. This is the sum of the series here, and so if we look at this, the x is just a 1/3. So the sum of this series here is the natural log of 4/3.